Okay. So hello again. I would like to talk today about Mongo clusters and more specifically how to connect to Mongo clusters that are built on top of Kubernetes clusters and how we can build such solution based on Kubernetes and additional DNS proxy that we developed in Allegro and open sourced. So let's start with the agenda. At the beginning, I would like to talk a few words about myself. Next, I will talk a little about Allegro tech platform to set the scene for the further consideration around the Kubernetes and Mongo and the cross-section between them. Next, I will talk a little about why the MongoDB is so popular as the database for microservices in Allegro, and why we decided to shift this workload to Kubernetes. And finally, we will go to the clue of that of today's presentation. So we will go step by step to show how the connection between the nodes within the Mongo cluster are made, and how to connect to such Mongo cluster from external world. And last, I talk a little about our pitfalls regarding this approach which we made. Okay, so here you have my LinkedIn profile if some of you would like to connect later. I'm a software engineer I'm engineering manager formally, but I'm previously was the software engineer and DevOps, and I still have hands-on experience with in such area. But I'm not database engineer and I'm not network engineer. So if you heard some incorrect information here, so be understanding to me. The main domains where I'm interested in are reverse proxy and web application firewall. This kind of layers are managed by my team in Allegro. All traffic that is handled by microservices in Allegro comes throughout reverse proxy layer that is responsible for routing traffic to particular microservices. And now I would like to take some about the principles how we build infrastructure in Allegro. First of all, we use multi-regional active-active approach. That means every microservice and every component of our architecture is distributed across data centers. We have 2 physical data centers, and we also utilize cloud providers. But to be more conscious, we focus here only on these 2 data centers. The multi-regional active-active approach means that if you are a developer who deploy your own microservice, you have to be prepared that a request that comes to even from the single user can be directed to one or the second data center. And so it means that the context and whole data connected with the user session have to be replicated between data centers to provide the user the consistent view of the platform. Second principle is high availability. It means that on each level we have a redundancy of components when it comes to the physical devices, when it comes to microservice instances, when it comes to whole data centers. And what we see here is a global server load balancer. It's a kind of DNS server that allows us to detect if one of DC is down and then switch whole traffic to another data center. In this example, our Poznań data center is down, so the global server load balancer detect that, and if user wants to resolve Allegro PL address, this address is resolved to IP that belongs to Krakow DC. And next principle that is consequence of the multi-regional active architecture is and service-oriented architecture. So using microservices for handling traffic is locality. Locality means that we are trying to process request that comes to one data center directly and only in that data center. It's because the latency between data centers isn't huge. When it comes to the milliseconds, it's only 8 milliseconds to round trip time between our data centers. However, to assembly the response for the customer, it may be, many microservices may be involved. So the communication between these microservices multiplied by the latency between data centers can be quite significant. So to prevent the latency, we try to handle whole traffic that comes from one request in single data center. And the last principle that we are trying to use is hiding the complexity before the microservice and before the developers. So here the good example is the service mesh. The service mesh is the part of the part of our infrastructure that is involved to in communication between microservices. Whole communication goes through the service mesh, and that communication involves a lot of processes that includes establishing secure connection, verifying if two sides of the connection are the proper one, handles retries, circuit breakers, and so on and so on. So from the microservice perspective, if microservice A wants to communicate to microservice B, only what it needs to do is to prepare HTTP request, and that request is intercepted by service mesh out proxy, and whole communication, establishing whole communication, is beyond the microservice. So to wrap up the microservice world, we have Kubernetes as compute platform for microservices. Microservices are usually stateless because managing replication and state is quite inconvenient, let's say. Microservice instances are registered in Discovery Service. However, Discovery Service is not queried directly by microservices because that it's not because Discovery Service is rather the source of the truth for control plane layer, which is responsible for configuring all components, basically service mesh and other communication components that participate in communication between microservices. Okay, so this is the stateless world. So let's check how it works with the data. So Allegro is quite complicated and big platform. We have a lot of variety of solutions that we used for storing data. However, on the purpose for today's presentation, we would like to look at the NoSQL world. And here we can see that the MongoDB solution outnumbered the Couchbase solution, which is second on the list. And we have around 1,000 clusters on prod environment distributed over 2 data centers, and also some of the workload is deployed on cloud providers. Why the MongoDB is so popular? There are many factors, but I would like to iterate 2 aspects. One aspect from developer and microservice perspective is ability to flexible go through the CAP triangle. So Mongo is designed in such a way that through the MongoDB driver you can prefer more consistency or availability depending what you need. And from the perspective of the maintaining such Mongo clusters, the maintenance overhead is significantly lower than in, for example, with Cassandra clusters. And we also have a lot of open source tooling that allows us to observe the clusters by, for example, Percona MongoDB exporter, and we also have support for compliance requirement, such as audit logs, which is not always available in another solutions. Okay, we can use for production purposes two kind of Mongo cluster types. First of all is the most popular in Allegro is replica set. It is a cluster that consists of nodes that can have three roles. Primary, which is used to write all data to the cluster. Secondary, which can be used for reading the data. And arbiter, which not hold the data but participate in the leader election. So in case of some disaster, for example, if the primary will be down, the node 2 and node 0, secondary and arbiter, can elect, in theory, the next primary in the cluster. And what is important here, all nodes have to communicate each other, so we have full mesh between the nodes that are part of the cluster. And another important thing that is tricky from the connectivity perspective is that the MongoDB driver have to know the topology of the cluster, because he needs to know where his queries that altered data should be directed, and where and which of the nodes are secondary nodes that can be used for reading the data. Sharded cluster is far more complicated and allow us to scaling the write throughput, because the data are splitted to shards, and in front of the shards is the Mongo proxy layer that splitting the queries to proper shards and later on joining the responses and serving it to client. And from the MongoDB perspective, from MongoDB driver, it is quite easy to handle such traffic, because MongoDB driver in such case doesn't know nothing about the topology of the cluster. He only uses Mongos, which are basically stateless proxy. Okay, so we know why the Mongo is popular, what kind of clusters we have. So let's take a look why we decided to shift such clusters to Kubernetes. Historically, the clusters were deployed on bare metal machines, and on each cluster we have a few databases. And in such configuration, there was one problem with the isolation. If one of the client overuse his own database, it causes the noisy neighbor effect. So all databases were affected by one client who overused his own database. To tackle this in Kubernetes, we decided to wrap each database. So each database has its own cluster, and we are not able to have so many physical servers to build such solutions. So we use Kubernetes that has quite good isolation between the pods. So the problem with the overuse, one pod, one cluster, doesn't affect the stability of other clusters. However, the small digression here, configuring limits for CPU is a little tricky in Kubernetes. What we see here is the pace of the logs generated by a single pod of MongoD. As you can see, there are some 100 millisecond windows in which at the beginning of that window we have for around 40-50 milliseconds some logs, and after that time there is flat, empty. There is no activity on that pod. And do you have idea what happened here? CPU limits were defined for that pod, and Kubernetes assumed that CPU limits are CPU are a resource that is compressible. It means if you use your resource in the first 50 milliseconds to the end of the settlement window, you won't be able to get any CPU anymore. So you never ever you should never set the CPU limits for the workload that is latency sensitive. And I also recommend to always log the real timestamps to be able to see such situation like that. Okay. So back to the Mongo on Kubernetes, we would like to reflect our old bare metal topology on Kubernetes. To achieve that, we need to build some nodes on independent Kubernetes clusters that are located in independent regions. And some insights around our Kubernetes on-premise clusters. We have independent clusters without any federation, without no overlay, a network which spans over the clusters. We also have pod IP addresses that are routable outside of the cluster, so you are able to connect to IP to pod directly using it IP. And we don't have load balancer and ingress resources available in our on-premise cluster. It means we are not able easily to expose service defined in the Kubernetes as a single IP that is available outside of the cluster. And having that, we have a challenge to build solution that will resemble that architecture. So to do that, we use approach based on native Kubernetes resources like stateful sets, services, job and deployments, but the stateful sets and services are the most crucial here. And our MongoDB replica set, don't confuse that with Kubernetes replica set. MongoDB replica set consists of host names. It means that the definition of the replica set is the list of the host names that connect each other. And the orchestration logic, so the logic that is responsible for building the cluster, configuring them at the beginning, is distributed in across external hooks, init containers, and our in-house operator. I put here asterisk because it's not per se operator. It's not running inside a Kubernetes cluster. It's outside application that communicates over API with multiple Kubernetes clusters. Okay, so to answer the question, where is my MongoDB? I divided this question to two aspects. First, where is my body? So how to connect between two nodes of the cluster. And secondly, where is my cluster? So how I can connect to such cluster from outside world, from my microservice, which is located outside of Kubernetes cluster. Okay, so let's try to build such solution like I depicted previously. So first approach is to deploy two stateful sets, each in each Kubernetes in different regions, and additionally add headless service that allows assigning stable network identifiers, stable host names for pods. Thanks to that, the pods can connect each other by its names within Kubernetes cluster. However, if we have two Kubernetes clusters and we spawn two stateful sets with the same name, we will have conflicted names, the same names, because by default, Kubernetes clusters have the same zone name. The zone name is the suffix of the name of the host names, and by default, this is cluster local. So, having four host names, where two of them are not unique, it's not feasible to build a cluster. So, how we tackle that? We just change the zone for each cluster, and thanks to that, we are able to have unique host names, even if we use the same stateful set name and the same service name. And the additional benefit is that we are able to recognize for what is the original Kubernetes cluster that possess particular host name. And I will talk about a little later with a diagram, which will be easier to comprehend that information. So let's imagine that we want to communicate with between two nodes of MongoDB that are deployed at the same Kubernetes cluster. In such way, our node just try to resolve the name of the second node in the cluster, and the logic in the Kubernetes DNS is simple. If this name which I want to resolve match to my internal zone, it will be Kubernetes KRA1 local. Then populate this host name based on Kubernetes metadata. In each other case, forward this query to upper level DNS. At upper level DNS, we mean here the DNS that stands outside of the clusters and can handle different kind of DNS queries. And how it is used in case of communication, of resolving the name between two clusters. In such case, the Kubernetes in the DC KRA region is not responsible for this host name. So this query is forwarded to upper level DNS outside of the Kubernetes. And in this upper level DNS, there is the logic that check to which cluster, Kubernetes cluster, the query should be forwarded next. So if there is Kubernetes POS local, it knows that this query should be passed directly to Kubernetes in Poznań region. And the resolution in the Poznań is the same like in Kraków. So now we are able to communicate within a MongoDB cluster that is spanned over Kubernetes clusters. However, that not solve all problems. We can use these host names in a standard connection string format, and it will be works. However, it's not preferred way to communicate between microservice or any client and Mongo. We can use alternative solution, SRV connection string, which are shorter, but also use the SRV records to dynamically check which nodes are part of the cluster. I will describe it a little later. Thanks to that solution, we are able to reflect the cluster changes on the MongoDB driver without recreating or reconfiguring connection string. Moreover, we can change either the host name of the cluster without changing the connection string. And the last but not least, we are able to provide only healthy nodes during the resolution of the name. So even if one of the nodes is in maintenance state, the resolution of the resolution of the service domain can provide only the nodes that are currently healthy, not in the maintenance state. So let's try to prepare spoof such records to be able to connect from MongoDB driver to cluster. So the simplest way is to add a new record cluster A Kubernetes cluster set local and point these records to original host names that are provided by Kubernetes headless service. But it turned out that such solution will not work, at least with MongoDB. Because there is a strong limitation that the name of the cluster and the name of the host name need the same parent domain. So we can't use cluster set and Kubernetes CRA local here. So to solve that, we also need to rename the host names in order to have the same parent domain for the name of the cluster and for each host name that is part of the cluster. And additionally, the new host names need to resolve to the same IP like original host names that were generated by headless service. Okay, having such configuration, we are able to connect from outside the world to the Mongo cluster that is spawned on 2 different or 3 different Kubernetes clusters. However, the maintaining such records can be not easy, and maybe we can use some other approach. And here is small digression related to reverse proxy word. A few years ago, we have monolithic app that generates all views that you can browse in Allegro. And we go to the point where we decided to move to the service-oriented architecture. And the first idea how to divide our monolith is to cut the parts of the interface and prepare thereby some microservices, let's say. And how it works. The monolithic app in such a situation generates HTML response that contains some SE tags, and that SE tags are by reverse proxy, which stands in front of the monolithic app and microservices, will parse the content returned by monolithic app and generate sub-requests to the URLs pointed in these markups, and later on replace the content of replace the original markups with the content returned by responses generated by microservices. And we would like to make something very similar when it comes to the DNS records. However, reverse proxy doesn't work well with DNS. So what we can do? We made some research, and we know that DNS servers can rewrite records in flight. We know that DNS servers can forward the query to different servers, even multiple. When one failed, it can resend the query to another. However, we can't find any solution that will be able to split query into multiple queries and merge them in flight. However, it turned out that Core DNS, that is the default DNS server for Kubernetes, has nice extendable architecture. So we prepared some plugin as supposed to verify if we can generate such records in flight without maintaining them directly. And how it works? Simply, microservice that wants to communicate with the MongoDB cluster use the name that we show earlier, and that query is split into two queries. To Kubernetes cluster in one region and the second region. And what is also more important, this query is rewritten to the format that is accepted by Kubernetes in a particular DC. So the cluster A Kubernetes cluster set local is rewritten to two queries, one to the cluster A Mongo service Kubernetes CRA1 local, and the second to the post local. And similar logic is performed on response. So if we got response from such to Kubernetes DNS, we rewrite these records to achieve the consistent top-level domain, and also prefixing the host names to be distinguished by MongoDB driver. So here we have the snippet of the configuration, and our plugin Gather SRV is configured to handle all requests that are in Kubernetes cluster set. And for each such request, the request is divided into two requests, and the Kubernetes cluster set is replaced with the first parameter. And on the response, the opposite replacement take place, and additionally, the prefix is added to each host name. And finally, we have the consistent approach. We have one domain which represents cluster and 4 records that were gathered from kube DNS, which are unique and also represents each node. And what is also important here, we also have we need to have ability to resolve a single host name as an IP address, because the MongoDB driver needs the IP address to establish the connection to the appropriate node. So the logic of resolving the single node is easier based on the prefix. The plugin knows that the query is about should be routed to a particular Kubernetes DNS, make some replacement, reread the query. When the response arrived, it rewrite response and return the IP address that can be used by MongoDB driver to connect to the node. So having that, we deployed such pods on production, and 1 year later, when the MongoDB on Kubernetes were widely adopted and the new connection string were widely adopted, finally the MongoDB on Kubernetes were crossed out from the exception list on our disaster recovery test, and turned out that during such test, the microservices can't resolve names of Mongo clusters because of timeouts. And why? Core DNS provides timeouts plugin that allows us to configure timeout, how long we can wait for the response from the whole server, and this timeout is passed to plugins as a context. But it turned out that forward plugin that is responsible for forwarding the splitted query to the next Kubernetes DNSs doesn't respect that timeout. So we handling timeout directly in our plugin before calling the forward plugin. So we were able to respect the timeouts And thanks to that, during this disaster recovery test, we are able to provide responses for cluster service domains that contains only nodes from a cluster that wasn't off. Because during this disaster recovery test, we basically turning off whole one data center. So there was no possibility to connect to that data center. So this DNS proxy that we prepared were not able to communicate with that data center. Another problem that maybe not problem but optimization that we made is removing the TXT and IPv6 AAA records. It turned out that those records are not supported on Kubernetes. We don't use IPv6 as Kubernetes for addresses for pods in Kubernetes, and additionally TXT records are also not supported as a part of headless service in Kubernetes. However, in the specification of MongoDB SRV string, there is ability to pass additional options to connection string by TXT records. You don't need to type these options manually to connection string, that they can be provided by such record, but in our case we can't use that. So using another plugin in Cortenes, we are able to generate the empty responses for such request directly from CoreDNS without passing them to the kubedns that was responsible for particular domains. So it allows us to save some milliseconds during the startup of MongoDB driver. And the last but not least, we are able to replace our sequential logic that was depicted on the diagram with parallel one. It was also important in case of disaster recovery test, especially when we switched from 2 Kubernetes cluster to 4, so the timeouts of each query were doubled during the test. So the parallel subqueries allow us to limit that latency. And finally, this is the view of our last disaster recovery test. It was take place last Monday, and as you can see, the P99 response from the server was capped by the timeout that was configured in the CoreDNS configuration. And here is also interesting that the time of waiting for forward query was quite low. It because that is view from the DNS server, which was in active data center, so it can't communicate to another data center. So he gathered only the data from the local data center, so the time dropped from around 50 milliseconds to around 3. Okay. There are some links if someone is interested with details how it works in Kubernetes operators that are community operators or enterprise operators, and also how what are the plans relating to multi-cluster services API, because that problem, it's not the thing that only Allegro faced. There is a lot of problems with putting the workload that is spanned over multiple clusters and the connectivity between the cluster, between the pods in the same the same cluster, but physically spanned on different Kubernetes clusters. And that's all from my side. I will be grateful for your feedback or in inventory. If you have any question and we have time, I'm happy to answer.